So previously, we have defined the covariant derivative of a vector field along a curve in terms of connection. Now we're gonna give another characterization in terms of parallel transport, and these two are equivalent. So to motivate this definition, let us explore what's difficult about defining derivative of vector field along a curve. Let's say we want to define the derivative of, we have a vector field V, right, and along this curve, and we want to define the derivative of this vector field at the point gamma t naught. Now, if we naively just copy the usual definition of derivative, we would say we'll take the limit of this quotient. We take vt minus vt naught, right, divided by the time difference, and we just take limit as t approaches t naught. Now, what's wrong with this? Well, even though this sounds good, and it looks okay because the picture is misleading, in reality, this difference here is nonsensical because these two vectors lie in different tangent spaces, right? So vt lie in the tangent space at gamma t, whereas vt naught lie in the tangent space at gamma t naught. We can't just add and subtract vectors from different vector spaces. So this expression, as is nonsense. However, not all is lost. We can fix this. So the idea is as follows. So what we do is that we move it, we transport this vector all the way to here so that these two vectors lie in the same tangent space. This is called a parallel transport of this vector. Now these two vectors lie in the same tangent space, so we can talk about this difference. The covariant derivative of v then, it's just going to be defined to be this limit, right? The limit of this difference as t approaches t naught. Right, so now we want to understand more about this parallel transport. We want to give a formal definition of this. So we say that a vector field W along some curve alpha is parallel if its covariant derivative is constantly zero. Now, using existence and uniqueness theorems about solutions of ODE, we can show the following: that if we are given a curve gamma on the manifold and a tangent vector here at some point gamma t naught, then it can be extended to a unique parallel vector field on the curve. Here I will just use the following notation to denote the unique parallel vector field along the curve gamma induced by this vector w naught. Using this, we can now transport tangent vectors between tangent spaces. So let's say we want to transport vector from this tangent space at gamma t naught to gamma t. You can define the following parallel transport map. It will take every vector w, extend it to a parallel vector field along gamma, okay, and then send it to the value of this parallel vector field at the point gamma t. Thus the image of this w here is this vector here in this picture. The inverse of this map then take this vector to this vector and put this in the same tangent space. This then allows us to define the, so we pull these vectors back to the same tangent space and we can take this difference. We form this quotient and the limit gives us the covariant derivative of this vector field along the curve t naught. A geodesic then can be thought of as a curve whose velocity vector field is parallel along the curve. For example, on the Euclidean space, the velocity vector field, all the velocity vectors just they have the same direction and magnitude. And on the look at the great circle on the sphere. So for a geodesic, if we know the velocity at one point, we can just transport it parallel everywhere and we get the whole velocity vector field. Alright, so that's how we define covariant derivative of a vector field along a curve using parallel transport.